Hello, everybody. My name is Ignacio Becerril Romero, and I'm going to speak about the use of spectroscopy and machine learning in the thin film PV industry. This presentation is about the work that I am performing inside of the Malmo project, which is an techno-sprint industry project which is financed by Acció and the Generalitat de Catalunya with Marie Curie funds from the European Union. My main objective in this presentation is to give you some key details about different points, which are the importance of photovoltaics, what is thin film photovoltaics and why it is related to nanoscience, and then about process monitoring from the thin film PV industry and how to use spectroscopy and machine learning in it. And finally, I will give you an example of a real application of these concepts inside of the Malmo project. Our society and financial system, they need an increasing amount of energy to sustain themselves and to keep growing year after year. Currently, our economy is powered by fossil fuels because they are cheap. We need cheap energy to avoid the collapse of our financial system. However, fossil fuels are finite, and they will approach depletion in the next decades, as you can see here. And additionally, their burning is increasing the CO2 levels in the atmosphere, which is causing a severe climate change. So how can we keep powering our society, but in a sustainable way? Renewable energies have a high potential to reduce our dependence on fossil fuels for electricity generation in a clean way. Among the different renewable energy sources, sunlight has the highest potential for electricity generation. We can use photovoltaics to convert directly sunlight into electricity. Just to give you a rough idea, with the sun power that arrives to the surface of the Earth, that it is convertible into electricity, which would cover the world yearly demand in only one day. Currently, PV technologies are based on silicon, which are the typical panels that you can see in the roofs of the houses or in the solar farms. This is a mature technology with a high efficiency, high production, and dropping prices. So it has a very high potential to substitute fossil fuels in certain applications. Okay, this is very nice, but what has photovoltaics to do with nano? Every PV technology relies on nanolayers. Even conventional silicon photovoltaics, you can see here the typical architecture. You can see that it uses layers, some layers which are as low as 5 nanometers. However, in general, the devices are around from 200 to 500 micrometers. This makes that the devices are rigid, fragile, and heavy, which limits their application to typical applications like self-sufficient houses or solar farms. And also has a high embedded energy for their production and a high production cost. Then we have thin film PV technologies in which we change the absorbent material by a material with a very high absorption coefficient, which allows reducing the devices from the macro microscale to the nano microscale. You can see here the typical architecture in which every layer is below 2 microns, and it can go as low as just a few nanometers. Thin film PV compared to conventional silicon PV presents a lower efficiency because it's not such a mature technology. However, the fact that we are going towards the nanoscale allows to make advanced production processes with low cost and low embedded energy. And also it allows to fabricate the devices on different substrates like flexible substrates that allow advanced applications and customizability and integrated applications like in vehicles, in consumer electronics, in buildings, even you can make transparent thin film photovoltaics. However, the problem of thin film technologies is that they are very complex. They are multi-layer. You can see here that our thin film PV device is a stack of different layers that are also multi-scale. Some of them are in the nanoscale, some of them are in the microscale. And also each of these layers is comprised by different elements. And each of these layers also has different control parameters. And finally, the production of each layer requires different techniques that have many different parameters. These parameters need to be controlled very precisely because we are working in a very small scale. So any deviation in the process can lead to manufacturing defect. This means that, okay, we have thin film PV, which is an advantage towards compared to conventional PV. However, we have the problem that the fabrication it's complicated. So what can we do to deal with this? We can use process monitoring. This means that the industrial production of thin film requires process monitoring. Okay, so what is process monitoring? Process monitoring is simply the implementation of inspection techniques in a production process that can monitor the production and detect deviations. And what are the requirements that the techniques, the inspection techniques need to have to be able to be used as process monitoring in the thin film PV industry? Well, first, they need to be fast, and they need to be compatible with the production speed. That means that they need to obtain information in a range going from seconds to around 1 minute. Also, they need to be contactless and non-destructive. Also, of course, they need to be sensitive to production and material parameters, so they can really be useful to detect critical deviations. And finally, they need to be easy to integrate in the production lines. So what techniques are compatible with these requirements? Light-based or optical techniques. They comply with all these requirements. This takes us to the next section, spectroscopy. You need to know that every material emits a characteristic light upon excitation. And if you analyze this light, which is characteristic of its material, it can give us information about its fundamental properties. Here you can see that we excite the material, it emits lights, and we collect this light. So what can we do with the light that we collect from these materials? Well, the most simple thing is to have a very simple detector in which we just measure the intensity of this light. However, this gives us very little information. We want more information, we need to add a diffractive element that decomposes the light in different components, and then to have a detector that can give us the intensity of its light component in its wavelength of energy, and with this we obtain what we call an spectrum. And from this word, from a spectrum, comes spectroscopy. Spectroscopy is to characterize or inspect materials using light-based techniques. Here you have some examples of common spectroscopic techniques like Raman, photoluminescence, X-ray fluorescence, and here you have the type of information to which they are sensitive. This is information such as the crystal structure, the composition, the doping on effects. So all these parameters, finally, they determine the final device performance. And as you can see, not every spectroscopic technique is sensitive to all the parameters, but they are quite complementary. The parameters that one technique cannot cover, they are covered by other techniques. This means that if we combine several techniques, spectroscopic techniques, we can get a very complete picture of the material properties. How can we use spectroscopic data for process monitoring? Well, first, let's take a look at how spectroscopic data looks. It's basically some shape with some peaks, with different positions, different intensities, etc. If you're a scientist, probably you have worked with spectroscopy before, and you know that the usual thing to do is to try to correlate the characteristics of the spectra, the number of peaks, their position, their shape, with the fundamental properties of the materials. However, in process monitoring, we don't care about the fundamental properties of the materials. What we need to do is to use the spectral data to detect deviations from the standard manufacturing conditions in a production process. This means that we need to correlate the spectroscopic data to the quality or the performance of the final device that we are fabricating. So the information obtained for process monitoring should be basically if the process is okay or not okay, although it can be more complex than this. So, okay, we have the spectroscopic data and we have the information that we need to get, if the process is okay or not okay. But what do we need to get this information? We need process monitoring methodologies. Conventional methodologies, which are analytical methodologies, they consist on the following. First, you analyze a small set of reference samples with known quality or known characteristics, and what you try to do is to extract relevant features in what we call a quality control parameter. Then you try to correlate this quality control parameter to the performance of the quality of the final device. Here you can see a very simple example in which you have a linear correlation of the quality control parameter with the device performance. And then what you need to do is from this correlation to develop a model based on this quality control parameter and validate it with known samples. In this case, the model will be very simple and will be just that when the quality control parameter is above a certain level, the process is okay. If it's below that level, it's not okay. But usually it is much more complex than this. Okay, now that we know what is process monitoring and that we know what is spectroscopy and how do we need to make methodologies to use spectroscopy for process monitoring, let's move to machine learning. What is machine learning? Well, machine learning is a branch of artificial intelligence algorithms that are specialized in classification. So we have what we call features and targets. Features are basically the data. Here it could be, for example, some shapes. And targets are the classification categories. Here it would be it is a square, a cross, a circle, or a triangle. Okay, so how does machine learning learn? So it learns through training. And what is training? In training, you have data that you have already labeled. So here you have different squares, different circles, different triangles, different crosses, and we label them with their category. They are square, circle, triangle, or cross. This is what we call our training data set. Then, in the training, the algorithm identifies patterns or relevant features that can explain the variability of the samples in this complex data. And with this, we have our machine learning model. Once we have this machine learning trained, we just put some input data, and then the algorithm will know, well, will let us know, will classify it according to these categories. Okay, so how can we use this for process monitoring? In process monitoring, the features or the data would be the spectroscopic data, would be the spectra that can be measured with one technique or with several techniques. And the targets, the classification categories, would be the process is okay or not okay in the most simple case, or it could be a little bit more complex than that. And how do we use these methodologies for process monitoring? Well, the methodology in this case is much simpler. First, we take the algorithm and we train it with a large set of labeled reference samples with known quality or performance. So, for example, we introduce this spectrum and we say this is for a process that it is okay. Or this other, and we say to the algorithm, this is a process that it is not okay. Then the algorithm looks for patterns and learns, and then what we need to do is to test this algorithm with samples from which we also know the quality of performance. And with this, we have our machine learning model trained and validated. So what are the differences between using analytical or machine learning methodologies for process monitoring? Well, in the case of analytical, it is fast and precise, does not require a large set of reference samples for their development, and they are based on quality control parameters that have a physical meaning. However, the drawback is that you need quite high knowledge in spectroscopy in order to be able to work with the data. You also need to be very careful how you condition this data to avoid any mistakes. And also the problem is that this is not flexible to changes in the manufacturing line. If you change a process, then you need to start all over again and create new methodologies. However, machine learning, the advantage is that it's simpler than analytical, it's fast and precise. You don't need any knowledge in spectroscopy. You don't need any kind of data conditioning. You can use the raw data in the algorithm as features. And also it is flexible regarding changes in the manufacturing line. In this case, you would only need to retrain your algorithms and you would get an updated methodology. The problem is that you require a very large set of reference samples for training the algorithm in a reliable way. And also that it is a black box. We don't have access to the quality control parameters that the machine learning finds for process monitoring. I hope that now, more or less, these concepts are clear, and I'm just going to show an application example for the thin film PV industry of these concepts. We have the company Sunplug. They have a thin film production of flexible PV modules in roll-to-roll configuration. This means that you start with a roll of material, flexible roll of material, of substrate, sorry, and you end up with a flexible roll of PV devices. And these are the type of PV devices that they produce, that they are flexible and they can be customized. And they have an spectroscopic characterization platform with Raman photoluminescence and X-ray fluorescence. And what they need to do, they want to do, is to map the quality of the material in an early production stage before or to avoid the fabrication of bad PV modules. So what we are doing in the project is the fabrication and analysis of reference samples with the different techniques of the characterization platform. And then we are training different machine learning models and evaluating them. So you need to take into account that this data, they have more than 1,000 dimensions. They are comprised by more than 1,000 points. It's a spectra. So with the machine learning, what we are doing is to reduce their dimension and then classify it. And this allows us, here you have a real example, to classify it in good quality, mid quality, and bad quality, going from 1,000 dimensions to only 2 dimensions. So this makes much more easy to work with the data. And then what we are also doing is, once we have the algorithms trained, we are using the PV production of the company to inspect it, and using the machine learning algorithm, we are able to map the quality of the roll. Here you have a real example of real measurements in which the green dots are parts of the roll that have a good quality, and the bad parts of the roll, they are marked with red spots. So this means that the application is useful and is working for the industry. So finally, some conclusions. First conclusion is that PV is fundamental for the world transition toward renewable energy. Then that thin film represents an evolution of photovoltaics towards the nanoscale that enables lower cost and advanced integrated applications. However, despite these advantages, the high complexity of these devices requires that the industrial production uses process monitoring to avoid manufacturing defects. Then we have learned that the spectroscopic techniques are very powerful for process monitoring of the thin film PV production, because they are fast, reliable, non-destructive, and sensitive to relevant material properties. And that the use of a spectroscopy in process monitoring requires the development of methodologies that can relate the spectroscopic data with the final device performance of quality. And in this regard, machine learning that has high classification capabilities can be used for process monitoring, simplifying the process of developing methodologies. Finally, we have shown that in the Malmo project, we are currently demonstrating the potential of these concepts for the thin film PV industry in a real case scenario. So I would like to thank you all for your attention. So to thank the Malmo project, Acció de la Generalitat de Catalunya, and especially to my colleagues in IREC that have made possible this work. Thank you very much. Bye-bye.